Hello everyone, and welcome to today's presentation. I am Pubali Sarkar, an assistant professor in the Computer Science and Engineering Department. Today, we will be exploring the fascinating topic of single linked list. Over the course of this presentation, we'll cover the fundamental concepts, how it works, and its applications. I'm excited to take you through this journey, so let's get started. Let's take a closer look at what a linked list actually is. A linked list is a type of data structure that allows us to store data dynamically, meaning we can add or remove items as needed without worrying about predefined sizes. This flexibility makes linked lists very efficient for managing data that changes frequently. Typically, a linked list in its simplest form starts with a null reference, indicating the end of the list, and then has a header, which is like the starting point of our list. Throughout this presentation, you'll see how this structure helps us handle data more effectively, especially when compared to other data structures like arrays. Understanding linked lists gives us a foundation for exploring more complex data management techniques later on. Let's take a closer look at linked lists and some of their key features. First, there's a pointer called the header, which points to the very first element or node in the list. This header acts as the starting point for traversing the list. Next, the nodes themselves are connected through pointers. Each node points to the next one in the sequence. This connection allows us to navigate through the list efficiently. When we reach the last node, it points to null, indicating the end of the list. One of the most flexible aspects of linked lists is that they can grow or shrink during the execution of a program. Unlike static arrays, they are dynamic in size. This means we can add or remove nodes as needed, making the data structure very adaptable. Because of this flexibility, linked lists can be made as long as necessary, without wasting memory space. They only consume exactly what they need at any given moment, which makes them efficient in terms of memory usage. Overall, these features highlight why linked lists are such a powerful and versatile structure in programming, especially when dealing with data that changes size frequently. All right, let's walk through the process of creating a new node in our linked list. First, we allocate memory for the new node by calling malloc and casting it to a pointer of type struct node. This is our new node. Then, we assign the data to this node by setting new node data equal to the data we want to store. Next, we set new node next to null, which indicates that this node currently doesn't point to any other node. Now, to connect this new node to the existing list, we set the next pointer of the previous node, which we've stored in temp, to point to this new node. This effectively links the new node to the chain. After that, we update temp to point to the new node, so that in the next iteration, we can add another node after it. When building a linked list with multiple nodes, say n nodes, we repeat this process n times. We allocate each node, read in its data, and adjust the links accordingly to form the chain. For example, if the data entered is 200, 50, and 30, the list will look like this: 200, then 50, then 30, connected in sequence. This process is fundamental because it allows us to dynamically create a linked list of any size, which is essential for efficient memory management and flexible data structures. Let's dive into operations on linked lists. Linked lists are fundamental data structures, and understanding how to manipulate them is key to efficient programming. First, I want to highlight that the main operations include inserting, deleting, and searching for elements. These are the building blocks that allow us to manage data dynamically. When we insert, for example, we can add nodes at the beginning, middle, or end of the list, which gives us flexibility. Deletion is equally important because it helps us remove data that's no longer needed, maintaining the list's relevance. Searching allows us to locate specific data within the list efficiently. Throughout this presentation, keep in mind that linked lists are powerful because they enable dynamic memory management, unlike static arrays. Understanding these operations thoroughly will help you see how linked lists underpin many complex data structures and algorithms. Now, let's explore some fundamental operations on a single linked list. First, traversing a list is essential. It's how we visit each node to perform actions like printing the data, finding the minimum value, or other computations. Traversal is the backbone of many linked list operations. Next, inserting a node into the list can be done at various positions, at the front, at the end, or anywhere in between. Understanding these insertion points helps us efficiently modify the list based on specific needs, whether we're adding new data or maintaining order. Similarly, deletion operations are crucial. Removing a node can happen at the front, at the end, or at any position within the list. Properly managing these deletions ensures the integrity of the list and prevents memory leaks or broken links. Comparing two linked lists is another important operation. We often want to determine their similarity, identify if they intersect at any point, or find common elements. These comparisons are vital in applications like data synchronization or detecting shared data. Merging two linked lists involves combining them into a larger list, either through union or concatenation. This operation is especially useful when consolidating data from different sources or building comprehensive datasets. Finally, ordering a list includes revering it or sorting its elements. Revering can be useful for backtracking or undoing operations, while sorting helps organize data for efficient searching or analysis. All these operations highlight the versatility of linked lists and their importance in managing dynamic data structures efficiently, reinforcing their role in solving various computational problems. Now, let's talk about traversing a linked list. Traversing is the process of visiting each node in the list one by one. It's a fundamental operation because it allows us to access or process every element stored in the list. When we traverse a linked list, we usually start at the head node and then follow the links from one node to the next until we reach the end, which is indicated by a null reference. This process is straightforward but important, especially when we need to search for a specific value, print all elements, or perform some operation on each node. Remember, the key concept here is following the pointers from one node to the next, which highlights the dynamic and flexible nature of linked lists compared to other data structures like arrays. This traversal process connects to the overall theme of understanding how linked lists work internally and how we can manipulate them efficiently for various applications. Now that we've constructed our linked list and the header points to the first node, the next step is to traverse the list. The idea here is to follow the pointers from one node to the next, displaying the contents as we go. Think of it like walking through a chain, where each node points to the next one in line. We keep doing this until we reach a node where the next pointer is null, indicating we've reached the end of our list. The traversal is handled by a function called traverseList, which takes a pointer to a node as its input. In our main function, we simply call this traverseList function and pass it the header pointer, which points to the start of the list. This way, the function can handle the process of visiting each node and displaying the data. This process is fundamental in understanding how linked lists operate, following the pointers sequentially to access all the data stored in the list. It's a simple yet powerful way to navigate through dynamic data structures like linked lists, which are essential for efficient data management in many applications. Let's take a closer look at how traversal works in a single linked list. The function traverseList takes a pointer to the header, or the first node of the list. The first key point is checking if the list is empty. If the header is null, it means there are no nodes to traverse, so we simply print that the list is empty. If the list isn't empty, we initialize a temporary pointer, temp, to point to the header node. Then, we enter a while loop that continues as long as temp is not null. Inside the loop, we print out the data stored in the current node, which is accessed via temp data. After printing the data, we move temp to the next node in the list with temp equals temp next. This way, we're advancing through each node sequentially. When temp reaches null, it indicates we've reached the end of the list and the traversal stops. This process highlights the core concept of linked list traversal. Starting from the head, visiting each node exactly once, and moving through the list via the next pointers. It's a fundamental operation that underpins many other linked list algorithms. Understanding this traversal method is essential for manipulating and processing linked list data efficiently. Let's talk about insertion in a linked list. When you're adding a new element, the process involves a few key steps. First, you need to identify where you want to insert the new node, whether at the beginning, the end, or somewhere in the middle. For inserting at the beginning, it's quite straightforward. You create a new node and point its next to the current head, then update the head to this new node. If you're inserting at the end, you'll need to traverse the list until you reach the last node, then link that node's next to your new node. For inserting somewhere in the middle, you'll typically traverse to the node just before the desired position, adjust the new nodes next to point to the next node, and then update the previous nodes next to point to your new node. This process highlights the flexibility of linked lists. They allow efficient insertions and deletions compared to arrays, especially when dealing with large datasets or dynamic data. Understanding how to insert nodes properly is fundamental to manipulating linked lists effectively, which ties back to our overall theme of understanding dynamic data structures and their advantages. Now let's discuss the steps involved in inserting nodes into a single linked list. First, you create a new node, which is essentially a container for your data and a reference to the next node. Then, you start from the header node, which is the entry point to your list. Managing links is crucial because it determines how your nodes are connected. Depending on where you want to insert, there are different scenarios. For inserting at the front, you link the new node to the current first node and update the header to point to this new node. To insert at the end, you traverse the list until you find the last node, then link it to your new node. And for inserting at any position, you locate the position where you want to insert, adjust the previous node's link to point to your new node, and then link your new node to the subsequent node. These steps are fundamental for maintaining the integrity of your linked list during insertion. Now, let's move on to the first step in inserting a node at the front of a singly linked list. The very first thing we need to do is create a new node. This involves allocating memory for the node and initializing it with the data we want to store. Think of this as preparing the new element that will become the new head of our list. Creating this node is crucial because everything else depends on having this new node ready to connect into the list. Once we have this node, we can then update the links so that it becomes the new first element, but step one is simply creating it. All right, let's walk through the process of inserting a new node at the front of a linked list. First, after creating the new node, the key step is to link this new node to the existing list. So, we make the new node point to the current head node. This essentially connects our new node to the rest of the list. Next, we need to update the head pointer itself. We make the new node the new head node, so that now the head points to this newly inserted node. This way, the new node becomes the first element in the list. Remember, the most important concept here is that the new node's link points to the old head, and then we update the head to point to this new node. This maintains the integrity of the list and ensures that our insertion at the front is successful. Connecting these steps to the overall theme, inserting at the front is a fundamental operation that demonstrates how we can efficiently add elements to the beginning of a linked list, which is essential for many list manipulations. All right, let's talk about inserting a node at the front of a linked list. The core idea here is to create a new node and make it the first element in the list. First, we allocate memory for this new node using malloc, which is essential for dynamic memory management. If malloc returns null, that means memory allocation failed, and we need to handle that gracefully by notifying the user. Assuming the memory is successfully allocated, we then set the data part of our new node to the value we want to insert. Next, we link this new node to the current head of the list by pointing its next to the existing first node. Finally, we update the head pointer to point to this new node, effectively making it the new front of the list. This process is quite efficient because it involves only a few steps: creating the node, linking it, and updating the head. It's a fundamental operation that demonstrates how linked lists are flexible and dynamic data structures. Remember, the key here is manipulating pointers carefully to maintain the integrity of the list. Now let's look at how we insert a node at the end of a singly linked list. The first step is to create a new node. It's important to set the address part of this new node to null, because this indicates that it's currently the last node in the list. So we do this by making new node next equal to null. Next, we need to find the last node in the existing list. We do this by traversing from the head of the list until we reach the node whose next pointer is null. Once we've found the last node, we connect it to our new node by setting last node next to point to the new node. This process effectively adds the new node at the end of the list, maintaining the linked structure. It's a straightforward but crucial operation for managing dynamic data structures like the singly linked list. Remember, the key points are creating the new node with null at the end, and then linking the previous last node to this new node. In this slide, we're looking at the process of inserting a new node at the end of a linked list. The function we're examining is called insertNodeAttend, and it takes an integer data as input. First, we create a new node using malloc to allocate memory dynamically. It's important to check if the memory allocation was successful. If malloc returns null, we display an error message. If the memory is allocated successfully, we assign the input data to the new node's data part and set its next pointer to null, because this will be the last node in the list. Now, to insert this node at the end, we need to traverse the list to find the current last node. We do this by starting from the head and moving through each node until we reach a node whose next pointer is null. Once we find the last node, we link it to our new node by updating its next pointer. Finally, we display a success message. This process highlights how dynamic memory allocation and pointer manipulation work together to add elements to the end of a linked list, which is fundamental for understanding how linked data structures operate. Let's walk through the steps to insert a node at any position in a singly linked list. First, we need to create a new node. This is the starting point, as we always need a fresh node to insert. Once we've created the node, the next key step is to traverse the list to reach the position right before where we want to insert the new node. Specifically, we go to the N1 node, which is the node just before our target position. Now, the critical part here is connecting our new node properly into the list. We do this by setting the new node's next pointer to point to the node that originally followed the N1 node, which is the N+1 node. We accomplish this with the statement new node next equals temp next, where temp is our N1 node. This connection ensures the list remains intact and properly linked after the insertion. Remember, understanding these pointer adjustments is central to mastering linked list operations, as they form the core of how data structures like singly linked lists manage dynamic data efficiently. All right, now we're at the final step in inserting a node at any position in a singly linked list. Here, we focus on connecting the new node to the existing list. The key idea is to link the node right before our new node, which we call the N1 node, to the new node itself. This is done by setting the next pointer of that N1 node to point to the new node. So, essentially, temp, which is our reference to the N1 node, now points to the new node by writing temp next equals new node. This action completes the insertion process, seamlessly integrating the new node into the list. Remember, this step is crucial because it ensures the list remains properly linked and accessible. Connecting the last node to the new node confirms that our insertion at any position is successful and maintains the integrity of the linked list structure. Now, let's look at how to insert a node at any position within a linked list. In this example, we're specifically inserting a node in the middle of the list. The first step is to create a new node, which we do by allocating memory dynamically. If the memory allocation fails, we handle that gracefully by printing an error message. Once the new node is successfully created, we set its data part to the value we want to insert and initialize its next pointer to null. We also set a temporary pointer to point to the head of the list, which helps us traverse to the correct position for insertion. This approach allows us to insert a node precisely where we want in the list, which is a key operation in linked list management. It's important to understand how dynamic memory allocation and pointer manipulation work together here, as they form the backbone of efficient linked list operations. This method ensures that we can insert nodes at any position, making our linked list flexible and adaptable to different data management needs. Let's walk through how insertion at any position works in a linked list. The core idea here is to traverse the list until we reach the node just before the position where we want to insert. We do this using a loop, starting from the second node and moving forward until we reach position -1. During this traversal, if we encounter a null pointer before reaching our target, it means the position is beyond the length of the list, and we can't insert there. That's why we check if temp is null after the loop. If it is, we know insertion isn't possible at that position. If temp is not null, it means we've successfully reached the node just before our desired insertion point. Now, to insert the new node, we adjust pointers. First, we link the new nodes next to temp's next, effectively placing it in the chain. Then, we update temp's next to point to the new node, completing the insertion. Finally, we provide feedback. If the insertion was successful, we print a success message. Otherwise, if we couldn't reach the position, we inform that insertion at that position isn't possible. This process highlights the importance of careful traversal and pointer updates to maintain the integrity of the linked list. Let's talk about deletion from a linked list. This is a fundamental operation that helps us manage data efficiently. When we want to remove a node, the key is to carefully update the pointers so the list remains connected and intact. The most important concept here is understanding how to locate the node you want to delete, whether it's at the beginning, the end, or somewhere in the middle. For example, deleting the head node requires updating the head pointer to the next node. If you're deleting a node in the middle, you'll need to find the node just before the one you want to remove, so you can adjust its next pointer to skip over the deleted node. And for deleting the last node, you'll need to traverse to the second last node and set its next pointer to null. Throughout this process, it's crucial to handle edge cases, like what happens if the list is empty or if the node to delete isn't found. Overall, understanding deletion helps us maintain and manipulate linked lists effectively, which ties into the larger theme of dynamic data structures and their flexibility in managing data efficiently. Now, let's talk about deletion in a single linked list. The key steps involved in deleting nodes start by beginning at the header node, which is essentially the first node in the list. From there, we need to carefully manage the links between nodes to ensure the list remains intact and properly connected after deletion. You can delete a node at the front, which is usually straightforward, by adjusting the header pointer to the next node and freeing up the memory. Similarly, deleting at the end involves traversing to the second last node, updating its link to null, and freeing the last node. Deletion at any position within the list requires a bit more care. Finding the node just before the target node, changing its link to skip over the node to be deleted, and then freeing that node's memory. Throughout all these cases, the important concept is that once the node is removed from the list, we must free up that node as free space. This step is crucial in managing memory efficiently and avoiding leaks. By mastering these deletion steps, we can keep our linked list dynamic and flexible, which ties back to our overall theme of understanding how linked lists operate and are manipulated in data structures. When working with dynamic memory allocation, it's crucial to remember that after you delete a node, you also need to free the memory associated with it. This is something that the programmer is responsible for. It's not handled automatically. If you forget to free this memory, it can lead to what's called a dangling pointer. That's a pointer that points to memory which is no longer in use by your program or the system. And here's an important point. The contents of that freed memory are not erased automatically. Until you overwrite that memory, it still contains whatever data was there before. This can sometimes lead to unexpected bugs if you accidentally access that memory later on. So always make sure to free your dynamically allocated memory after deleting nodes. It's a good practice to prevent memory leaks and ensure your program runs efficiently and safely. This ties back to the overall theme of managing resources carefully in C programming. Proper memory management is key to robust, reliable code. All right, let's walk through the steps to delete the first node of a singly linked list. First, we start by copying the address of the first node, which is the head node, into a temporary variable called toDelete. This is important because we need to keep track of the node we're about to remove. Next, we move the head pointer to the second node in the list, which is done by setting head to head next. This effectively removes the first node from the list, as the head now points to the second node. These steps are fundamental for understanding how deletion at the front works in a singly linked list. By first saving the address, then updating the head pointer, we ensure that the list remains connected and consistent after the removal. Now, moving on to step 3, we need to disconnect the connection of the first node from the second node. Essentially, we're updating the pointer of the first node so it no longer points to the second node, which is a crucial step in deleting the first node from a singly linked list. Once we've done that, we arrive at step 4, where the next important task is to free the memory that was occupied by the first node. This step is vital because it prevents memory leaks, ensuring that the memory used by the deleted node is properly released and can be reused for other purposes. By understanding these steps, we're effectively managing how nodes are removed from the list, which ties back to our overall theme of efficient list management and memory handling in data structures. Let's take a look at how we delete the first node from a linked list. The function is called delete first node. Essentially, what we're doing here is removing the very first element in the list, which is often a common operation when managing linked lists. First, we declare a pointer called toDelete. This will help us keep track of the node we want to remove. Next, we check if the list is already empty by seeing if head is null. If it is, we simply print a message indicating that the list is empty, so there's nothing to delete. If the list is not empty, we assign the current head node to toDelete. Then, we move the head pointer to the next node in the list. This effectively removes the first node from the list structure. We then display the data that was stored in the node we're deleting, so we know exactly what was removed. After that, we free the memory that was occupied by the node to prevent any memory leaks. Finally, we print a message confirming that the first node has been successfully deleted. This process highlights the importance of updating the head pointer and properly freeing memory to maintain an efficient and safe linked list. It's a fundamental operation that illustrates how linked lists are dynamic and flexible in memory management. All right, let's walk through the steps to delete the last node of a singly linked list. First, we need to traverse the list to reach the very last node. As we do this, it's important to keep track of the node just before the last one, which we'll call the second last node. We can do this by maintaining a temporary variable, say second last node, during our traversal. Now, once we've reached the end, there's an important check to make. If the last node happens to be the head node itself, that means our list has only one node. In that case, we simply set the head to null, effectively deleting that sole node. But if the list has more than one node, we disconnect the second last node from the last node by setting second last node next to null. This step is crucial because it removes the reference to the last node, allowing us to delete it and maintain the integrity of the list. These steps are fundamental in managing linked list operations, especially when we consider how to handle edge cases like a list with just a single node. It ties back to our overall theme of understanding linked list manipulations efficiently and correctly. All right, now we've reached the final step in deleting a node at the end of a singly linked list. After we've updated the second last node to point to null, the last step is to free the memory occupied by that last node. This is a crucial part because, in programming, if we don't release the memory, it can lead to memory leaks, which can cause problems down the line. So, we simply deallocate or delete that last node from memory, ensuring our program manages resources efficiently. This step completes the deletion process, making sure our linked list remains clean and optimized. Remember, properly freeing memory is essential whenever we remove nodes in dynamic data structures like linked lists. Let's take a look at how we can delete the last node of a linked list. The function is called delete last node. First, we declare two pointers, toDelete and second last node, both starting at the head of the list. The goal here is to traverse the list until we reach the last node, which is where toDelete will end up. During traversal, second last node trails behind to keep track of the node right before the last one. We do this using a while loop that continues until toDelete's next pointer is null, indicating we've reached the end. Once we're at the last node, we check if toDelete is the head itself. If it is, that means the list only has one node, so we set head to null, effectively emptying the list. If not, we disconnect the second last node from the last node by setting second last node's next pointer to null. Finally, we free the memory occupied by toDelete, removing the last node completely. This process ensures that we correctly handle both the case of a single node and a longer list, maintaining the integrity of our linked list structure. All right, let's walk through the process of deleting a node at any position in a singly linked list. The first key step is to traverse to the nth node, which is the node we want to delete. During this traversal, it's important to also keep track of the node just before it, the N1 node. We typically store this reference in a temporary variable, which we can call prevNode. This way, once we reach the target node, we have both the node itself and its previous node handy for the next step. The second crucial point is to reconnect the list after we've identified the node to delete. We do this by adjusting the next pointer of the prevNode to point to the node following the one we're deleting, which is the nth node's next node. Essentially, we're bypassing the node to delete by linking prevNode directly to delete next. Remember, toDelete is the node we want to remove, and toDelete next is the node that comes after it. This reconnection effectively removes the target node from the list. By doing so, the list remains intact, and the node at the specified position is successfully deleted. This process highlights the importance of careful traversal and pointer adjustment, which are fundamental in managing linked list operations efficiently. It also ties back to the broader theme of understanding how linked lists are dynamic structures that require precise pointer manipulation for modifications. Now, in step 3, we're focusing on freeing the memory occupied by the nth node, which is the node we want to delete, also known as the toDelete node. Once we've adjusted the links to bypass this node, it's essential to deallocate the memory it was using. This step helps prevent memory leaks and keeps our program efficient. Remember, in linked lists, managing memory properly is just as important as updating the pointers. By freeing this memory, we're ensuring that the node is completely removed from the system and that resources are properly managed. This step ties back to the overall theme of dynamic memory management and efficient data structure operations. Now, let's look at how to delete a node at any position within our linked list. The main idea here is to remove a node from anywhere in the list, not just from the beginning or the end. The function we have, delete middle node, takes a position as its parameter. First, we check if the list is empty by verifying if the head is null. If it is, we simply print a message indicating that the list is already empty because there's nothing to delete. If the list isn't empty, we initialize 2 pointers, toDelete and prevNode, both starting at the head. The goal is to move to the node we want to delete, which is at the specified position. We use a for loop starting from 2 up to the position, updating prevNode to point to toDelete, and toDelete to move to the next node each iteration. It's important to handle the case where toDelete becomes null before reaching the desired position, which means the position is beyond the length of the list. In such cases, we break out of the loop to avoid errors. This approach ensures we have a reference to the node we want to delete and its previous node, which is crucial for adjusting the links in the list properly. Overall, this method provides a flexible way to delete nodes from any position, which is a key part of managing linked lists efficiently in our overall data structure management. Now let's look at how deletion works at any position in a linked list. If the node to delete, represented here as toDelete, is not null, we proceed. First, we check if toDelete is actually the head of the list. If it is, we update the head pointer to the next node, effectively removing the first node from the list. Next, we connect the previous node, prevNode, to the node after toDelete by adjusting prevNode next. This bypasses the node we want to delete. Then, we set toDelete next to null to detach it completely from the list. The critical step is freeing the memory occupied by toDelete with the free function, which prevents memory leaks. After that, we print a success message indicating the node was deleted from the middle of the list. On the other hand, if to delete is null, meaning the specified position was invalid or the node doesn't exist, we print an error message stating that deletion is not possible. This process highlights the importance of carefully managing pointers during deletion to maintain the integrity of the list and avoid errors or memory issues. It ties back to our overall theme of understanding linked list operations thoroughly.